Hello students, welcome to this module on module 3 of the course CH3 614 on hydrodynamic stability. In the last two modules what we have done is to introduce you to the subject and sort of motivated the reason why we study hydrodynamic instabilities and gave you some very classical examples of laminar to turbulent transition and other flows where there are instabilities. Now what I'm going to do first in the next few modules in this course is to discuss or introduce you to a topic that may be called as discrete dynamical systems or nonlinear dynamics. It's a very brief introduction to a very vast subject, so that you understand, you can get some intuition as to why things are unstable, how new solutions emerge and so on in the fluid mechanical context. Okay, so first remember that the governing equations of fluid flow are partial differential equations, PDEs, right? The Navier-Stokes equation, for example, the momentum equation looks like this. Is minus grad P plus mu del squared V. Let's not worry about body forces for the moment. If you look at this term, this is nonlinear because it involves products of the unknown and their derivatives, right? So we are interested in understanding how a given solution becomes unstable in the context of Navier-Stokes equations, which are partial differential equations, nonlinear partial differential equations. Now these are much more involved in terms of the mathematical techniques involved, right? So these are much more detailed. Now in order to gain some intuition and gain some familiarity with what could happen in nonlinear systems, I'm going to discuss these ideas in the context of ordinary differential equations, nonlinear ordinary differential equations. Okay, and this subject is called discrete as opposed to continuous. Remember that in Navier-Stokes equation, velocity is a continuous function of x, y, z and t, and therefore these are velocity fields are fields. They are smoothly varying functions of all the coordinate directions and time, whereas in the examples that I'm going to consider, we are going to consider ordinary differential equations where the spatial dimension doesn't come at all. So for example, you may have dx1 dt is equal to some function 1 of x1 x2. You may have a system of ordinary differential equations, nonlinear. This is some other function and so on. These are system of this is an example of a system of coupled nonlinear ODEs, where in general the functions are nonlinear functions f1 f2 and I goes from, so I can generally write this or condense this whole thing as dxi dt is some fi of x1 to xn. Okay, and this is, you may also have time in this function. You may also have time explicitly occurring in this function. You know that all these dependent variables x1 x2 themselves are functions of time, but in addition you may have time occurring explicitly. Okay, so here also let me include that for the sake of completeness. This is called a dynamical system. Such a system of ODEs, okay, in the language of modern mathematics, is called a dynamical system. Okay, and now one may just for the sake of illustration, you can think of three variables x1, x2 and x3. These are the three dependent variables. x1 is a function of time, x2 is a function of time, x3 is a function of time. Okay, now you need to supply initial conditions because these are ordinary differential equations. So I imagine, suppose I have this axis x1, x2, x3 of the dependent variables. I imagine giving an initial condition at some point, and then if you were to numerically solve these differential equations, then the solution will be wandering in this three-dimensional space, right? And this three-dimensional space is called a phase space. Okay, these are all terminologies that come from physics and mathematics. So this is called a phase space, and this is the initial condition. You may say that x1 at time t equal to 0, x2 at time t equal to 0, and xa at time t equal to 0, such that they appear at this point, and then you can numerically solve these, and this is called the phase trajectory. Okay, now you can also generalize these to higher dimensions, but then we may not be able to plot them so easily, but for lower 3 dimensions it's easy to plot. Okay, now there is one more jargon that I would like to introduce, that is that of non-autonomous versus autonomous ODEs or dynamical systems. In a non-autonomous system, okay, the functional forms FIs on the right side will have time explicitly appearing. Whereas in autonomous systems, FIs do not have times, the time variable t, the independent variable which is time, explicitly appearing. Okay, now you can always suppose I have this let's say I have dx dt is x1, sorry, dx1 dt is x1 squared minus x1 time. This is an example of a non-autonomous ODE. I can always convert a non-autonomous ODE to an autonomous system of one higher order by simply saying that let x2 is equal to t. That means dx2 dt is 1. Okay, so I will add one more equation, dx2 dt is 1, and instead of dx1 dt is x1 squared minus x1 t, instead of t I will put x2. So this becomes an autonomous system because time is not implicitly occurring, but you have the cost of increasing the order by 1 because initially you had only this equation, right? x1t, this is non-autonomous, but this can be made autonomous by increasing the order of the system by 1. By order I mean the number of differential equations in that you have in your problem. Okay, now for those of you who have done chemical process control, process dynamics, you are familiar with writing down models, ordinary differential equation models for reactors and so on. For those of you who are in mechanical engineering, you are familiar with this from your dynamics classes, that you have several models in terms of ordinary differential equations. Okay, now so this is the simplest notation, dx dt is equal to sum f of x. This can be in general nonlinear. This is an example of a representation of a dynamical system. Okay, now one simple example, physical example that we can think of is a damped nonlinear pendulum. Okay, so you imagine you have a point in which you have a string and then you have a pendulum, right? And this is the vertical, the direction of gravity, and this is theta, right? And you know that this is g sine theta, and you know that this is g cosine theta. Okay, now if you write down the equation for the angle theta, then you will find that d squared theta by dt squared, and it is damped, so there is some damping. So I have this damping coefficient which slows down the pendulum as it oscillates, plus omega naught squared sine theta is 0. This is an example, this is a physical example, a simple differential equation that describes a damped pendulum. It is nonlinear because it has sine theta in it, so this is the nonlinear term. Okay, now you can write this in the dynamical system format by saying that x1 is equal to theta, x2 is equal to d theta dt. If I do this, then I will get dx1 by dt is x2, then dx2 by dt is equal to minus mu x2, x2 is just dx1 by dt, minus omega naught squared sine x1. So this is a nonlinear system of two differential equations. It's nonlinear because of the presence of sine x1. Okay, this is an example of how one writes a differential equation in a second order differential equation in the form of two coupled first order differential equations. Okay, let me write it properly. Okay, this sine term is nonlinear. I say coupled because the equation for evolution of x2 has x1 in it. Okay, and the equation for evolution of x1 has x2 in it. So this appears here, whereas this appears here. So they are coupled. So you cannot solve them separately. You have to solve them simultaneously. Now, in general, this dynamical system of this form, this ordinary differential equation system that represents a dynamical system of this form, fi of x1 xn. Okay, let's assume that we have an autonomous system, because you can always convert a non-autonomous system to an autonomous system by redefining the time variable. Okay, let's consider an autonomous system. Okay, this is in general I equals 1 to n. This is an n dimensional system, or a system of nth order. Okay, so instead of going to nth dimensional system, let's start with the simplest possible dimension, which is one dimensional system. Okay, n is equal to 1. So this is called a 1D system or a first order system. Okay, right. So here the only variable we have is x. Okay, so it is defined, its time evolution is described by dx dt is f of x. It's an autonomous system, so time cannot appear explicitly here. There is only one variable, so dx dt is f of x. Let's assume f of x to be a smooth real valued function. Okay, now in dynamical systems you often write dx dt as x dot of t. So x dot is dx dt. Okay, time derivatives are denoted by a dot on above the variable. Okay, so now let's understand how in general, for if you have n variables, you have what is called a phase space of n dimension. If you have a three-dimensional system, we just saw in the previous slide that you have three variables, right? The phase space becomes a three-dimensional space, and then you can worry about how trajectories are wandering in the phase space by solving the equation. Right now, in 1D, the phase space is really a phase line because there is only one dimension, in which x can, there is only one dependent variable x, there is nothing else, right? So how do we understand nonlinear dynamical systems in 1D. That is the objective of the rest of this module. Now let's consider an example. Let's consider x dot is equal to sin x, okay, with some prescribed initial condition. Okay. By the way, this part of just the introduction to dynamical systems, I follow the book by Steven Strogatz. It's called Nonlinear Dynamics and Chaos. Okay, it's a very elementary. There is a very nice discussion on whatever we are going to do, but I am going to do a very elementary discussion of what is given in the book. But for further reading, you may wish to consult that book. Okay, now if you were to solve this exactly, you may get a solution. It's not often that nonlinear equations have solution. You have to be lucky to get some a solution. Here you get a solution. This is cosecant of x naught plus cot x naught, where x naught is the initial condition, by cosecant x plus cot x. Now this is not a closed form solution, it's an implicit solution, in the sense that you want x as a function of t, but this is giving you t as a function of x. Okay, so but nonetheless there is some solution in analytical form, but it is so difficult, the functional form is not easy to interpret analytically. So what one does in nonlinear dynamics is to plot qualitatively what is going to happen. So let me illustrate this example. So we have x dot is equal to sin x. Okay. Now in this is not the phase plane or phase line. Here I am plotting x. So this is the phase line, the x-axis. The y-axis is actually x dot, which is simply f of x. So that is a dynamic. I am plotting the rate of change of x as a form. dx dot is nothing but dx dt, right? On the y-axis I am plotting simply x dot is equal to f of x. By definition, that is our differential equation. Okay. Now I am going to plot the sine wave. Okay, it keeps going. Okay. Now whenever you have, let's mark these points, whenever you have x dot, whenever x dot crosses 0, okay, let me mark these points. There is a reason why I am plotting some as filled circles and some as empty circles. I'll come to that in a minute. But so whenever this f of x function, which is sin x in this particular case, right, f of x is, I'm simply plotting x dot is sin x, because x dot is sin x in our example here, right? That is our example. Whenever you have a 0 crossing, that means x dot is 0, right? That means that is a steady state solution. Okay, that is a steady state solution. In the language of, this is what you call in fluid mechanics or transport phenomena, that when you get a solution that's independent of time, you call it a steady state solution. In the language of nonlinear dynamics, these are called fixed points, because once a solution hits there from some initial condition, you will just stay there. Now we can understand let me just rewrite a little bit here. Okay, this should go here. Now this this should go here. I'll come to that in a minute. This should go here. Okay, let me just draw this. I'll explain what these are in just a moment. Okay, now imagine in this phase line I'm starting off. Let me use a slightly different color. I'm starting off from here. Okay, this is my initial condition at time t equal to 0. Now obviously I need to supply in order to some x naught. I'm saying that this is my x naught. Now the question is, in which direction this point is going to go. Okay, that's the question. Now if you look at this corresponding to this x naught, the initial velocity is dx by, I'm using the term velocity loosely. This is the rate of change of the variable x, which is what is the initial velocity of, let's say, that variable, right? Now that is positive, right, corresponding to, if you choose a value here, right, dx by dt initially is at time t equal to 0 sine x naught, and because x naught is in this range, it is positive. Okay, so if dx by dt is positive, that means this variable is going to go in this direction. Now it will go all the way and then it will hit this point. Now this is a fixed point. Once you hit here, you cannot go anywhere, because now from then on time derivative is 0. So you will find that I'm sorry about this. You'll find that any point, not just here, any point lying anywhere here should go all the way, because the velocity is all positive in this direction, and then stay here. Likewise, if I choose any point here, okay, any point in this range, let's say here, let's say I take a point here at time t equal to 0, if this is x naught, then the corresponding dx dt is negative, so the points will move like this and then come to this fixed point. Now we can keep doing this. If I choose any point in this range, the flow in the phase line will be in this direction. If you take any point in this range, it will be in this direction, and if you take any point in this range here, in this range here, and so on. So all we are doing is to just look at where your initial condition is and look at its corresponding time derivative, and if it is positive, from this graphical construction we are plotting the time derivative as well. If it's positive, you go right. If it's negative, you go left, because dx dt is negative, means x will decrease with time. Okay, now what is the meaning of such fixed points, where if you start anywhere here, all these points, any initial condition in this direction will go here, any in this direction will go here, and then once you hit this point, you will stay put there. Such is called a stable fixed point. Such a fixed point is called a stable fixed point. Why is it stable? Any point, if you go away from this fixed point, you will go only towards the fixed point. On the other hand, the filled circles are stable fixed points. Open circles in this figure are unstable fixed points, because if you are on that fixed point exactly there, then of course you will be there, you will be staying put there, you cannot change, because dx dt is 0 there. But any infinitesimal region away from this fixed point, you will start going towards some other fixed point. That means such solutions are unstable, and some people call these as these are attractors and these are repellers. because they repel any neighboring initial condition gets repelled and it goes all the way to the other stable fixed point. Okay, these are also attractors, also can be thought of as sinks, and repellers as sources of flow in the phase line. Okay, so this is a very qualitative way of understanding what happens to this simple dynamical system. Now we can also try to plot the evolution of the solution. So here I am plotting sorry about this. Here I am plotting the evolution of x as a function of time. Okay, now from the previous so this is x is 0, x is pi, okay, this is 2 pi, this is 3 pi, this is minus pi, minus 2 pi, minus 3 pi, and so on. Okay, this is a sine function. Now if x is between 0 and pi, so let's say x is pi by 4, okay, this is x equal to pi. Now without even going into the details of the solution, we know that this solution will go and eventually touch this and then stay there. Okay, this is x naught is pi by 4, the initial condition, right? It will go all the way, it will and then settle at x equal to pi. This is what we just saw in the other illustration, qualitative illustration just now. Okay, now if x is between pi and 2 pi, right, just give me 1 minute. Okay, this is pi, so this is pi, this is 2 pi, this is 2 pi, right? Skip the pi here. Okay, now any initial condition between pi and 2 pi, because 2 pi is an unstable fixed point, sorry about this, let's use the same color, so it will again come and then it will eventually settle down at pi. Okay, of course if you start above 2 pi, it will go to the next closest stable fixed point. Okay, now while I introduced this qualitative ideas in the simple context of x is equal to sin x, we can generalize it to any function x dot is equal to sin x. We can generalize it to any function x dot is equal to f of x in the following manner. If we just know the functional form of f of x, let's say this is the way f of x is. So this is x dot is f of x. The f of x is this function. Okay, this is x. Now we can see immediately how many fixed points are there. There are 2 fixed points. Okay, now we can again see which are stable fixed points, which are unstable fixed points. Now if I look at this fixed point, now if I go a little bit away here, right, then the velocity is positive, so the flow is in this direction. If you go a little bit away from this from the same fixed point to the left, the velocity is negative, the flow is going to be in this direction. So this is an example of an unstable fixed point. As opposed to this, here if I start from here, anywhere in this region, things are going to go in this because velocity is negative. Anywhere in this region, velocity is positive, so things are going to move in this direction. So this is a stable fixed point. This is an unstable fixed point. Okay, so fixed points will be denoted as x star they are independent of time, and they are variously called these solutions, invariant solutions, are variously called fixed points or steady state solutions or equilibrium points, and so on. There are many names for such things. Now, so far we have developed a qualitative understanding of how things are evolving and how to characterize a given fixed point as stable or unstable. Now we can make this a little more quantitative by a very simple method called linear stability analysis. Okay. Now this is going to give a little bit more quantitative information about the stability or instability of a fixed point. Let x star be a fixed point of the dynamical system, 1D dynamical system. X dot is equal to f of x. Now we want to know whether this is a stable or unstable fixed point. We don't want to plot it the way we just did. We want to do it more mathematically. Now let x of t be x star, which is the fixed point, plus eta. This is a deviation from the fixed point, okay, or perturbation. So eta is simply x of t minus x star. Okay, so d eta dt is nothing but dx dt minus dx star dt, but this is 0 because x star is a steady state. It's a fixed point, doesn't change with time. So I substitute this back in the equation. We had x dot is f of x, so we have d eta dt instead of x. This is the same, this is x dot, so instead of x dot we have d eta dt. So instead of f of x, I'm going to write it as f of x star plus eta. Okay, because this implies that x t is equal to x star plus eta. Okay, now I'm going to Taylor expand the right side of this equation. F of x star plus eta, that's nothing but f of x star plus f prime, which is a derivative with respect to x at x star, times eta plus f double prime of x star by 2 factorial eta squared plus so on. Now f of x is by definition 0 because that is the definition of steady state. Remember, you had that dx dt is f of x, so f of x star becomes dx star dt, which is identically 0. Okay, if I put a star here, then this is 0 for fixed points. Okay, so you have d eta dt is nothing but, if I assume small deviations, then eta squared is much small compared to d eta if mod eta is small compared to 1. These are very small perturbations from the steady state. Okay, so d eta dt is nothing but f dash of x star times eta plus higher order terms which are neglected. Okay, so this is a very simple, and this is just a number because this is a derivative of f of x evaluated at x star, just a number. So I can easily integrate this. So this is nothing but eta of t is eta at time t equal to 0 e to the f dash of x star t. Okay, this is very simple to solve. So if f dash x star is greater than 0, then the fixed point should be unstable because eta is growing exponentially with time. If x dash of x star is less than 0, then the fixed point is stable. This is precisely what we found in our graphical analysis as well. When you have a positive, if you have a fixed point, if f star is at that point is if f dash of x star is less than 0, it is stable. Is greater than 0, it's unstable. So if you see here, this is greater than 0, so it's unstable. If you see here, this is less than 0, f of df dx at this point at the fixed point is actually negative, so it's stable, whereas here it's positive, therefore it's unstable. Okay, that's what we have written here. Okay, so you might ask the question, what if f dash of x star is 0? Then of course we cannot say anything within the linear stability analysis. You have to do what is somewhat more involved. You have to do some nonlinear analysis to understand what's happening in reality. Okay, now in addition, this tells you that f dash of x star should have dimensions of 1 over time, right? And this tells you that or 1 over f dash of x star will tell you the time scale for the characteristic time scale for growth or decay of perturbations. Okay, so this is the advantage of the linear stability analysis, wherein you get additional information. Okay, so what if f of x star is 0? So let's look at some examples. Suppose I look at x dot is equal to minus x cube. Okay, and here x equal to 0 is a fixed point. Okay, now if you plot the function, it will look like this. Okay, so even though this is a there is no f prime of x star is 0, just by graphical construction we can figure out that this is a stable fixed point, although this cannot be concluded from a linear stability analysis. Similarly, x dot is equal to x cube will be an unstable fixed point. Okay, because just by graphical construction you know that if you plot f of x, okay, versus x, you will find that this is unstable, because out here dx dt is positive, so things will fly away in this direction. Out here dx dt is negative, so things will fly away in this direction. And if you have x dot is equal to x squared, then you have a situation like this. So on one side velocity is positive, it's unstable. On the other side it's stable because velocity is negative. So this will be the trajectory. If you come from this side, this point is stable. If you come from this side, this point is unstable. This is called half stable. Okay, and if x dot is 0, then any point is a fixed point, so on the x-axis, and perturbations will neither grow or decay. Okay, so this is all that we can infer from one-dimensional systems. What one-dimensional systems tell us is that how the phase trajectories evolve in the phase line in 1D space, and how once the phase trajectory hits a fixed point, then it will stay put there. And if you have a stable fixed point, even if you perturb the fixed point about its original value, it will come back, all the perturbations will decay. Whereas if you have an unstable fixed point, any slight perturbation will lead trajectories to fly away from this unstable fixed point. Okay, I'll stop here for this module, and I'll again start from a new topic on bifurcations in the next module. Thank you.